Hello everyone, today I'll make a presentation about MRI sequences and I'll basically focus on TOF MRI. As you know, there are lots of MRI sequences used to visualize different parts of body. Some are used to image brain, some are used to image upper parts of body. There are lots of techniques for that. For example, diffusion weighted imaging is one of these techniques. Volumetric interpolated brain examination is another one, or short tau inversion recovery is also one of them. But today I'll basically focus on TOF MRI, its time of flight effect. It can be considered as like that. MRA, it's also known as magnetic resonance angiography, is a group of techniques in magnetic resonance imaging. It uses magnetic field and radio frequency to obtain the images of flowing parts in body like blood vessels, arteries or veins, and this technique mainly aims to evaluate abnormalities occurring in such places of body. The images acquired by using this technique are mainly focusing on flowing parts in body. These group of techniques called MRA are mostly used in arteries of brain, neck, thoracic and abdominal aorta. These places are mainly flow blood vessels. That's why these techniques are preferred. MRA techniques are generally divided into two groups. One is contrast enhanced and the other is non-contrast enhanced. Under non-contrast enhanced group, there are several techniques. One of them is phase contrast imaging. The other one is time of flight. And this presentation will mainly focus on time of flight effect and we'll explain deeply about it. TOF effect occurs during magnetic resonance imaging due to some flowing particles in human body like blood in blood vessels. These effects mainly give rise to some changes in magnitude of magnetization at those points with flowing spins, and these effects result in some distortions in signal and maybe even a complete loss of signal can occur. Therefore, TOF effect changes the signal intensities at those parts in body. However, this signal can be used as a favor in sometimes because during the imaging of moving parts in body like blood vessels, this technique is mainly preferred and I will explain how it is used. TOF effect depends on the difference between stationary spins and flowing spins in human body. Stationary spins can be considered as local tissues and flowing spins can be considered as blood vessels. It occurs since the spins excited in a selected slice flow out of the slice during the excitation time, and the spin that is excited can be lost after this excitation because there is a constant flow in this duration. As a result, TOF effect occurs. It has different impacts on different imaging sequences like gradient echo sequence and spin echo pulse sequence. So we will explain more about them. The effect of TOF will be explained deeply for these sequences. There are two main effects of TOF. First one is signal washout effect. It's an undesired effect. It mainly occurs in spin echo sequence. In spin echo sequence, only the spins that are exposed to both 90-degree and 180-degree RF pulse are used to obtain signal. Since the main condition for spins is being exposed to both of these signals, even complete signal loss may occur during these technique because if the blood flow is very fast, then it's nearly impossible to apply both of these RF pulses to the same spins because there will be a blood flow during these excitations, and then if the blood flow is not that fast, then some fraction of blood may experience both of these RF pulses. So some fraction of blood may experience second RF pulse in selected slice so that they result in given an echo signal. It is possible to lose the signal completely or instead some part of signal may be lost. Therefore it's called signal washout effect. It's mainly it can be observed mainly in spin echo. The effect is different in gradient echo sequence. Then now I'll explain it. Let's first talk about spin echo. In first RF, 90-degree RF, pulse spins are brought down to transverse plane and we generate signal, and stationary and flowing spins are starting to relax with T2 star relaxation time. When the second RF pulse, the 180-degree RF pulse is given, stationary spins start to recover same transverse magnetization. However, the flowing spins have left the slice. They won't be refocused with the second RF pulse and they will relax rapidly. The second set of successive RF pulses are considered, and new blood is coming to the selected slide, so we have a lot more longitudinal magnetization than the stationary spins. So when we apply the second set, the stationary spins are going to have lower magnetization than the flowing spins, so the TOF effect causes the stationary spins to get saturated after multiple RF pulses. And when we measure the signal at echo time TE, because of the inflow of the fresh blood, the inflow of the new spins, there's still going to be higher signal from the incoming spins than the stationary spins. The stationary spins are, as I've said, tissues, and the inflowing spins are blood vessels. So the tissue, the stationary spins will produce less signal than the flowing spins, because due to these multiple RF pulses in stationary spins, there will be saturation and they'll start to give less signal, they'll start to generate less signal and less magnetization. That is why the contrast will occur between them. Second effect of TOF is Gaussian enhancement. It's also known as inflow enhancement. It's a desired effect. This effect both occurs in spin echo and more significantly in gradient echo pulse sequence. If the signal washout effect does not occur, or in other way, if the blood flow through the selected slice is not that much fast, then inflow enhancement effect occurs. As in gradient echo pulse, after multiple RF pulses applied to the same selected slice, stationary spins which became saturated due to these multiple RF pulses is suppressed by flowing spins because they're saturated. And in selected slice, in each excitation there's new fresh blood coming in, so the new coming blood will be excited for the first time, so that the longitudinal magnetization will be higher in these spins. So these fresh spins produce relatively large signal compared to stationary spins. So previously excited blood and tissue that have longitudinal recovery won't generate so much signal. In gradient echo imaging, second RF pulse of 180 is not applied for recovery, for refocusing purpose. That's why signal washout effects are not observed in gradient echo pulse. However, inflow enhancement has a big role. It's a desired effect during the obtaining of images of blood vessels. So these Gaussian enhancement effect will be mainly focused during these TOF sequences. There are some key points to observe these TOF effects. First one is that the flow direction needs to be perpendicular to the selected slice to pass the flowing spins from inside to the inside of the slice. A parallel flow of bloods may result in loss of signal. Secondly, TR has also important effects. TR is the repetition time, as you know. TR needs to be relatively small. Also, the flow rate of blood needs to be small as well to have some fraction of blood to be excited, and fast flow of spins may cause the complete loss of signal. That is why these key points are important. TOF technique can be divided into two groups. One is white blood and the second one is named as black blood. In white blood, high signal from the flowing spins is obtained and low signal is from the stationary spins is obtained as well. In black blood, low signal from the flowing spins and high signals from stationary spins, tissues, is the main focus. So we'll basically focus on the white blood. In white blood technique, stationary spins suppresses the spins are suppressed with the flowing spins, and basically we give multiple RF pulses, and the tissues get saturated after multiple RF pulses and they appear dark, and the new coming fresh blood appears bright since it will be excited for the first time, and the washing effect will be important for this technique. In TOF technique, both 2D and 3D imaging is possible, and inflow enhancement has an important role during these imagings. In 2D imaging, inflow enhancement reduces with saturation, and saturation depends on number of RF pulses experienced by spins, and it needs to be adjusted very well for this technique. And it also depends on flow rate of blood. It depends on longitudinal recovery time, which is known as T1, and repetition of pulses, it is also known as TR. Saturation exposed by flowing spins can be set by adjusting these terms, so these effects can be minimized by using slices with smaller thickness and relatively long time of repetition. Advantages of using 2D imaging is we can set the slow flow, and it provides us better contrast between tissue and blood, and it means we get better signal. Generally, we use gradient echo sequence for 2D imaging of TOF technique. TR is preferred between 20 and 30 milliseconds, and tip angle is preferred between 50 and 70 degree. If the flow rate of blood close to critical velocity, then flowing spins experience a few RF, which means the saturation in blood vessels will be much less, so we'll get better contrast. And in 2D imaging, there's a little disadvantage, which is low spatial resolution. We have low spatial resolution. Let's talk about 3D. In 3D imaging of TOF technique, we have single slab of 3D slices, and the blood flow needs to be perpendicular to these slab of slices. In 3D imaging, there is a little disadvantage that we have high SNR, although we have high resolution, although we have high spatial resolution. So during these set of SNR and contrast of tissues and blood vessels, we need to set the slab thickness very well, and the number of slices in a slab are also important for this 3D technique. So that's all for my presentation. Thank you for listening.